Okay, good afternoon. Can you hear me at home, people at home? Hello? Uh, might be I cannot hear you, sorry. Yeah, once more, can you hear me?
Yes.
Thank you. Okay, so this last chapter of Mathematics 5 is actually going back to what you are familiar with. That's differential equation. We learned about differential equations a little bit in Math 4. In this session, I want to refresh your memory a little bit and solve some questions, and then we continue the rest of it tomorrow. So the lesson will end around 3:30 because I have a gymnasia RVT session. Okay? So what do we mean by a differential equation? An equation that contains an unknown function. So usually when I say solve an equation, for example, if I give you this equation and I ask you to solve it, you are not supposed to give me a function, you are just giving me a number or a bunch of numbers depending on the degree of the equation. So for example, here if I ask you what is a solution of this, you would say that x is equal to -2 is a solution, and you see -2 is just a number. But in a differential equation, and the unknown that you're looking for is not just a number, it's just a whole function, okay? That is the differential equation. Of course, an equation that contains an unknown function together with one or more derivatives of that function. It means that the first derivative, second derivative, or higher order derivatives. And there is a terminology going on here. The highest derivative, the order of the highest derivative, is called the order of the differential equation. So this word you need to know, the order of the differential equation. Okay, so this is something that you need to know. And instead of differential equation, I will write DE for short, okay? And then what do we mean by a solution? Any function that when replaced by the unknown function any function that when replaced by the unknown function turns a given differential equation to an identity is called a solution of the equation, of the differential equation. Okay, so we need to, these are some terminologies that you need to know. And then an important thing is that a solution that contains as many free parameters as the order of the differential equation is called the general solution of the differential equation. So you need to know what is the meaning of a differential equation. You need to know the notion of an order in a differential equation. You need to know what is the meaning of a solution to a differential equation. and you should also know what is the meaning of the general solution to the differential equation. Okay, actually, if the differential equations is a very important topic, because whatever you learn in science turns into a differential equation if you want to predict something about the behavior of the system in the future. For example, if you have the initial condition of the system at the moment and you want to predict what is happening for the system in a little bit later time, which is actually the main goal of science, or actually physics or whatever, because that's the only thing, that's the difference of science and philosophy. In philosophy, probably we cannot predict what happens even if we have all the circumstances right now. But in science, for example, physics, if we know the state of the system right now, and if we know the rule governing the system, then probably we will be able to predict the future of the system. And that is the whole strength of the new science and the new way of dealing with science. And most of the time, whenever you want to predict the future, it turns out that you have to solve a differential equation. So this is why it's extremely important. Okay, so for example, let us consider a problem from physics. Okay, so here you have, I don't know, this is your x-axis, and then you have a spring here, and then you connect a block of mass to it. So let us call this mass m. For simplicity, let us consider that this surface is well lubricated and there are no frictions, for example. Of course, if you want to see the real problems, you should still bring in the friction as well. But let us consider, for simplicity, there are no frictions involved here, and then assume that in this situation, so for example, let me consider this. Let me consider this the origin of my x-axis, for example. Assume that in the equilibrium, when this spring is not stretched nor squeezed, this block of mass is actually on 0. Yes, I call that point 0. And then what we do, for example, I stretch this a little bit so that the distance from the origin becomes x. Now, for example, I stretch it a little bit. So, for example, this spring is stretched a little bit, and now your block is a little bit farther away from this. And let us consider this displacement is x. Okay? And then I keep it in that situation, and then I release it. So what happens? This spring is actually pulling this block to the left, yes? And then this block will move here, because when it reaches here, it still has velocity. It will continue the movement, make this spring to be squeezed. And then when the spring becomes squeezed, the spring starts exerting force on this block in the other direction, pulling back, forcing it back, yes, to the equilibrium. So this will go forever if there is no friction here. Now the question is that my starting situation was here. For example, assume that my starting situation was, so let me write it in this way, x node, or let me call it x at 0. I pull it up to some point and then release it. Okay? The position of this block would be a function of time in the future because it goes back and forth. Yes? So my goal is that, can I predict this function? If you ask me, where can I find this block after 3 seconds? Can I answer this question? Where I can find this block after 5 seconds, 10 seconds, or 1 million seconds, if the system situation, the state of the system remains the same. So it goes back and forth. But of course, it is clear that you need to be able to predict where would be the position of this particle or this block at a later time t. So that is the point. This is a really, really simple setup. But if you want to answer this question, how do you solve the problem? So is it clear? I have this setup. In this situation where the mass is on the 0 of the x coordinate, I myself choose the origin of x coordinate to be here at the equilibrium. I pull it a little bit to the right until it reaches to some number, for example, say 5 centimeters or whatever. At that point, and then I start, I release it. I'm assuming that there are no frictions here. This will start moving back and forth because of the spring force. And then it becomes clear that I cannot ask where is this particle. I have to ask where the particle is at an instant of time. So that's my question. How we can answer this question? By the way, this is a very simple mechanical system, and it is a bit idealistic, yes, because I'm ignoring friction, even though here it's very well lubricated, but still there are some frictions that I cannot ignore. But assume if I bring them in, my model becomes more real, and then it becomes more complicated. But let us assume this simple system. How do you answer this question? Okay, so it's something. This is not something that mathematics can solve it, yes, because I mean mathematics can solve the problem after you know the law governing the system. If you don't know the law governing the system, then you don't know what to do, because you need to know something. You need to extract something from the universe by experiment to understand what is the law governing my system. Then that law is expressed in mathematical language. Then mathematics comes in and tries to solve that problem mathematically. And then when we got the answer, we interpret the final answer again physically. So you see, you have some law. It turns the physical system to a mathematical equation. You do mathematics in between and then find the answer. And then when you have your answer, you go back and interpret this answer in a physical way, yes, for this system or whatever it is. So probably you know a little bit of Newton's second law, yes? So if you want to see where the particle is in the future, so what do you know? So probably you have heard about this Newton's second law. This is the mass of the particle, and this is the acceleration of the particle, and this is the total force exerting on that particle, yes? So here, of course, there are some other forces. Here we have the reaction force. We usually denote it by N, even if we ignore this. And then we have a gravitational force, so that is M times G. G is the constant acceleration of gravity here. But this is on the Y direction. So what would be the equation on the Y direction? These two should cancel out, yes, because this particle is not moving up, it doesn't move down. So it tells you that N is equal to mg, but it is useless because it is even though it is true, it doesn't say anything about x for you. So then it becomes clear that if I want to know something about x, when I write the Newton's second law in the y direction, it becomes a trivial line. So it becomes n in the upward direction minus mg, but I do not have any acceleration on the y-axis, so it becomes the mass of the particle multiplied by its acceleration. But the acceleration on the y direction is 0, so this is why you get that n is equal to mg, yes? Even though it is true, but it is useful for predicting the value of n, not for predicting for x of t. So if I want to know something about x of t, then it means that I need to write Newton's second law on this direction. Yes? I don't know how much you know about vectors, because this is a vector equation. So it means that you can decompose it in any direction that you want to. If I decompose it on the y direction, this would be the result. And now I want to write these components on the x direction. Okay, now help me to do that. M is n. So I would write A equals to F, but this A, I mean the acceleration of the particle along the x direction. Okay, what can I write? So can you help me? So here, what can I write for F first? What is the only force acting on this block only in the x direction? Yes?
The force of the spring.
There is only one force. If you ignore friction, which I told you I'm ignoring that. Okay, do you remember Hooke's law? That is Hooke's law, yes? Have you heard about that? Yeah. So what is that? it would be some constant k, which depends to the material of this spring. How much is it stiff, or I don't know, is it loose? So yeah. So if you have a strong spring, then this constant is big. If it is a small, if it is actually not very strong, then k is a small. Okay, and then what should I put here? X. What should I put in front of k? Do you remember from your physics lessons? L. So in this, what is L? What is the interpretation of L? Yes, you are right. I think in physics probably they write it L. So KL. What is that L?
When the elongation of
The elongation. Yeah. So it means that the change. So this L is not the length of the spring. It's how much this spring has been stretched or squeezed. Yes. So in this language, it becomes x. Do you agree? Because I told you that in the equilibrium, I assume that it is in the origin. So when I move it to the right, it becomes x. By the way, there is a negative sign here, yes? Why is that? Because if I go to the right, x is positive in my formula. But then you realize that the spring is pulling this to the left. And when I go to the left, x becomes negative. But the spring forces it to the right. So this negative sign is because of that. Is that understandable?
yes.
Yes or no? So if I want to write it here, I have to write minus k of x. Because when you write a force, it is extremely important to consider the direction as well. If you don't consider the direction, it is not a vector, it's just a scalar. Okay, and then what can I write for the acceleration? Remember, my goal is to write everything in terms of x. So x at some instant t multiplied by k multiplied by negative sign give me the force along the x direction. M is just the constant mass of this block. And then I want to write a. Of course, I can write a, but I want to write everything in terms of my unknown, because I want to have one unknown to be able to solve for it. Okay, so what can I write for a? This is extremely simple. Probably I'm confusing you. So what is the relation between acceleration and the speed? Not the speed, the velocity. Now these things we need to know. We also talked about this in the math lessons, didn't we? Pardon?
Never mind.
So, do you remember when I was teaching you the derivative, I told you that what is the velocity of a particle?
Acceleration times time.
No, that is for only uniform case, in general. So,
Initial velocity.
no, you are only giving me the formulas for the very simplest case, the general case. So let me tell you something. So do you remember, if you want to find the instantaneous speed, for example, at some moment of time, this is, for example, t, and a little bit later t plus h. Yes. If I ask you, what is, so let me make it the x-axis. Assume that my particle is here when time is t, and it is here when time is t plus h. What is the distance traveled by that particle is the difference between these two. So the particle was here a little bit later time, the particle is there. So the displacement that this particle has gone through is actually this. Agree? This is the displacement. And if I divide it by h, this is the interval, this is the time interval between this instant of time and that instant of time. What is this one in physics?
The distance between the two.
Okay, divide. What is this quantity called? Average velocity. Yes, because if my particle moves with a constant speed, there is no difference between average velocity and instantaneous velocity. Yes. So this is not the velocity, because it might happen that my particle starts speeding up or speeding down between t and t plus h. So if I calculate this, there is no guarantee that this is the velocity of my particle here. But if I make this interval shorter, this becomes closer to instantaneous velocity of the particle at instant t. Yes? And then what does it mean by making this interval shorter? I mean that I am making h smaller and smaller. So it means that if I take the limit of h goes to 0, this is a reasonable definition of what we want to call the velocity of the particle at time t. Yes? And what is this one in mathematics?
So, Leibniz equation?
No, come on, what is this one?
The derivative.
This is the derivative of x. So this becomes the derivative. I write it in Leibniz notation, you are right, but this is nothing except the derivative of the position of my particle. Is that understandable? So, yeah, of course you said, what you said is correct. I would write it as dx dt. This is in Leibniz notation, but there's no difference. This is the derivative. And now if I ask you the same question for acceleration, how do you answer that? So, what is acceleration then? Because here I need acceleration to put it in this formula, yes? So what is the acceleration if you want to calculate acceleration in general? That's a general relation, you see? This tells you that if you want to find this velocity of a moving particle at a particular instant of time, if you know where the particle is as a function of time, this is so simple. What you need to do, just to take the derivative of that function. Yes? And now we want to do the same thing. What happens for acceleration? How do you calculate the acceleration? The idea is the same. What is the meaning of acceleration? Yes?
The change in velocity.
Change in velocity, yes. Now assume that the velocity of your particle at this instant of time is t. A little bit later, the velocity of your particle is this one. We don't know if this is bigger than this one, smaller, we don't know. But we know that this velocity has changed to this value during this interval h. Now if I ask you what I am calculating, if I just write this, what is this one called in physics?
The
Average acceleration. This is average acceleration. But again, the same story. If I take the limit and h to 0, this is a reasonable definition of the acceleration of the particle at instant t. Yes? And now, this is also the definition of the derivative, but the derivative of this function, which becomes v prime t. So what we learn is that velocity is the derivative of the position function, and acceleration is the derivative of velocity function. Yes? So what is the relation between acceleration and position now? It becomes evident, yes? What is that?
Second derivative.
Yeah, it is the second derivative. So you realize that acceleration is nothing except the second derivative. Yes? So now, if I take this one and put second derivative, this becomes an equation. This is the relation. A mathematician just by sitting in an island thinking about this, he will not be able to get this equation. It needs experiment. Yes? Okay? But after that, a mathematician is actually good playing around with this. Yes? Because this is a mathematical problem. And then you see that what is my unknown? What is my unknown in this equation? M is not unknown because I can measure the mass of my particle, so it is known. K is something not known. For example, the factory producing this spring will give you that constant by measuring it through different weights, yes? So what is unknown in this equation then? Yes?
T.
No. This is crucial. What is the unknown? Even T, you cannot say T is unknown because you are waiting. You cannot do anything. Yes, you just wait. Okay? If you are, and then you look at your watch. So T is, of course, it is passing through. You are passing through time, but T is, you cannot say T is the unknown. What was the unknown in the beginning? What I am supposed to predict?
X of t.
X of t. But do you think x of t is a number or not? X is a number which depends on t. So it means x is a function of t. And what you are looking to find is finding x as a function of t. So this is not a normal equation. It is an equation, it includes an equality. It is an equation because we are looking for an unknown, but it is not just a normal equation because I'm not looking for finding x, for example, x equal to 5, x equal to 3. I want to find x for every given instant of time. So I want to have infinitely many answers. Each x, I want to say that at time t equal to 1, here is my particle. I don't know, at t equal to 3, here is my particle. So if I want to solve that, be careful, I want you to understand. If I want to solve that, what should I write? I should find x for each instant of time. So this means that this is an unknown. If I ask you what is the unknown in this equation, you would say a whole function is unknown. Is the unknown, yes? So here the whole function x of t is the unknown. And then we need to, this is called a differential equation. Why? Because my unknown is a function, if you refer to my definition, I told you that an equation in which a function is the unknown, and in that equation the function and some of its derivative appears. So here the function x of t appears, and then suddenly the second derivative appears. But that is the differential equation that I want to solve. Yes? And now, so let me write this in a little bit nicer way. The way that in physics people do that, so they bring it to the left. So this becomes m x double prime t plus k x of t equals to 0. And then usually they divide by m. And this becomes k over m, x of t equals to 0. And in physics, there is a symbol for that, and that is called omega. This is called omega, so this means this expression is omega squared. This is just minor things to make it look more beautiful, but essentially there is no difference what I have written here with that one. And that's exactly the same angular velocity. You need to understand what is the interpretation from physical point of view, but let us just stick to this one. So that is your differential equation. So in principle, the situation, I don't know, if Newton just knew about this, but he was not able to solve this, it's completely useless. Yes? Because you are using this formula coming from experiment and thinking, and how to understand the law, you were able to reach to this equation, but then you are facing a math problem, how to find this x in reality, yes? If you cannot find and solve this equation, then you cannot predict even if you know what is the law governing the system. The law governing the system is the second law, but if you cannot solve it, you cannot predict anything. And this is the situation, and there is a bad news to that. Most of the differential equations we cannot solve. Okay? We cannot solve them exactly, but we can solve them to any desired accuracy that you need. So there have been methods developed for calculating this function to any desired accuracy that you like. But of course, this is not one of those cases. This is one of those cases that you can immediately calculate this. Yes? And find the answer. Okay, let me ask you now some questions. Can you somehow guess what would be a solution for this? Or what type of function you want? That is probably not a good question if I ask you what's the solution. But what type of function somehow you know that you can have something like this here, yes? Can you guess a function which more or less have this behavior? When you differentiate it 2 times, it more or less becomes equal to itself up to a constant, yes? Because omega is a constant, yes? If I write it in that way, yes?
E to the power of a constant.
Oh, okay, let us check. You are close, but there is a caveat for that. So how do you?
Maybe instead of e, we should use.
Because let me write e to the if I guess that x of t is some exponential function, I don't know which one. So what happens? I can give a number here as well, alpha. So if I differentiate it once, it's good because alpha goes down, and then I have e to the power of alpha t. If I differentiate it once more, somehow you see alpha squared comes in, and then e to the power of alpha t, but instead of this one, I can write x of t, so it becomes alpha squared x of t. So it means that, so Alex was not that wrong. Because the second derivative of an exponential function becomes a constant squared multiplied by alpha t, but something crucial prevents this guess to be correct. What is that crucial thing?
That e to the power of.
No, there is something crucial in the equation which prevents this to be the correct one. So if I start with positive alpha, yes?
You're adding two positive positive numbers.
No, I'm multiplying, I'm not adding. You want to say something?
It's the second derivative that should be multiplied by the
No, everything seems correct. You see, when I started with just an exponential function, when I took the second derivative, it has a good structure, yes? The second derivative is equal to a constant to power 2 multiplied by my function. The crucial thing is that in the one that I want, I have a negative sign there. You might say that, okay, let us start with negative here, but it doesn't work, yes? Because even if I start with a negative sign here, when I take the derivative, yes, the first one becomes negative. When I differentiate it once more, another negative alpha goes down, then it becomes positive alpha squared again. So it's this minus sign is actually crucial in prediction of what's going to happen. So we need to give up the hope. There is no hope for finding an exponential function as an answer. Mathematicians only think about this. But physicists, by the way, don't even guess this function. Why? Because in mathematics, we don't have the mother nature to say something to us. Okay? So mathematicians might, if you are pure mathematician, you don't care about the universe at all, might be you want to try this as well. Yes, why not? Because it was very close. But a physicist will never probably start with that. Why? Based on ideas that you have an intuitive way of thinking about the prediction of the system, you know that this system goes back and forth. So what's the problem if something like this happens? Do you expect that this system explodes suddenly? You just move it a little bit and then suddenly the system explodes. This will not happen intuitively from a physics point of view. If you have this kind of function, there is an explosion there, yes? If alpha is positive, what's happening when t becomes large? Assume that alpha is positive. When t becomes large, this exponential function goes to infinity. And this means x becomes infinitely long. And then you know that this is odd. This doesn't happen in the universe. So from physics point of view, you even don't need to bother about this solution. What happens, by the way, what happens if alpha is negative? Why this is not intuitively correct? Assume that alpha is negative. Not mathematically. This is the proof. Mathematically it doesn't work, yes?
X becomes 0.
X becomes 0. Actually, this is real. If I have friction there, you might expect that the system will stop somewhere there, yes? But if the system is frictionless, there is no reason that this will stop. Okay? But if I start with this and alpha is negative, when t goes very big, this becomes negligible. So it means that this will go and stop close to the middle, yes? Which is not probably true. It's very important to understand this both from physics point of view and from mathematics point of view. So I mean that even physicists doesn't bother to think about this when they think physically. Okay? But the point is that there are many various systems. For example, in quantum mechanics, we don't have intuition about how the system behaves. So the only thing that we can rely on is mathematics. Okay? So we have to rely on mathematics, and then we get some result, and then we test the result. If the results are the same, might be that's a good confirmation that we are on the right track. If we can see some discrepancies, then it means that we need to go and change the assumptions. Yes, that is the way that it works. Okay, is that understandable? But still, can you tell me what type of another function? So exponential functions was very close, but it was not that good. Can you guess something else? It's very famous. You have seen it, by the way, in physics. Yes?
Maybe like sine function.
Sine function. It's a good choice, yes? Sine function is a good choice. And by the way, you should be able to guess sine. Let me talk about these things to feel them. What is that system behave in reality, in your intuition? It goes back and forth. So what is happening? It repeats the same pattern over time. What is the analog of that in mathematics? The function is, yeah? Periodic. Yes? And the most famous periodic functions are sine and cosine function. So if you see it from physics point of view, might be you should be able to guess something about the behavior of the function. Yes? We immediately, intuitively, we realize this system will oscillate back and forth. And this means that it repeats its pattern. It means it's periodic. So it is better to, now you realize, even from mathematical point of view, that was not a good guess, because this exponential function is not periodic. If you remember the graph, it goes up or it goes, I don't know, the other way around. Okay? But sine function goes up and down. So that's a good choice. So, but can you adjust it for me? For example, can you guess something? People at home also can guess. So what can I guess for this? You said sine function, but I want exactly get this exact answer. Sine function is the type of the function. I agree with you. But what is the exact value for that? So I need to write sine is equal to sine. What should I write in front? So for example, I'm probably confusing. Do you think sine t is good? Let us do that. Take one derivative, it becomes cosine t. Take another derivative, it becomes minus sine t. So this is x prime, and this is x double prime. But what can I write? X double prime is minus sine t is x, so what I get is minus xt. It is close to my equation. You see, I need my minus sign, and it is here. But unfortunately, I do not have omega squared. Okay, can you now adjust to have the omega squared as well? So this function was close, but I do not have omega squared here. How can I adjust this function so that omega squared also appears? Your brain's freezed, I think, today. Yeah, it's late.
Sine omega.
Sine omega t. So why do you hesitate to say that? So let me write it here for you. Sine omega t. So x of t sine omega t. I want to come to a point that's important. Let us check this this educated guess. So x prime t is what? According to the chain rule, this becomes cosine omega t, but you have to multiply by the derivative, which becomes omega. Yes or no? And then I take another derivative. What is the derivative of cosine? Is negative sine, but I need to multiply by the derivative of this according to the chain rule, so it becomes negative omega squared sine omega t. Yes? Yes? And then what happens? X double prime of t, I put minus omega t squared. What can I put here? I can write this back again. So, do you agree that this guess was the right answer to this? Yes or no?
Yes.
Okay. Keep it here. Why not? Let us consider a cosine function. Okay? So let us this time consider a cosine function. for the same reason, let me start with cosine omega t. Yes? What happens now? X prime of t becomes minus omega sine omega t. Yes? And then x double prime of t becomes minus again omega squared cosine omega t. Yes? And then x double prime of t is equal to minus omega squared x of t, because this time this is x of t. Again, the same equation. Then how the system should decide how to behave. Do you understand what I mean? Because let us see. What do you predict? If this is if you see this is a solution, you also see that this is also a solution. For example, let us wait, I don't know, 5 seconds. Then what happens here, this will predict that the position of the particle is at sine 5 omega, yes. And of course, omega is something given to you. K is given, M is given, so omega is a number which is known to you. You multiply that number by 5, you take a sign, it becomes a number. It means that 5 seconds later, this particle should be here, according to this function. But let me calculate the same thing according to cosine function. So this becomes this one, do you agree? But these two are not generally equal. So where this poor particle should be after 5 seconds? The one predicted by this function or the one predicted by the other function? Do you understand what's the problem? So I come up with this differential equation, and then I haven't talked about how to solve that. We are guessing the solution. We talked about this, it was close, but it was not working. Then instead of having one solution, I have two solutions, which is working. But I hope that you agree with me, at any given instant of time, the position of the particle is unique. The particle, this is not quantum mechanics. The particle cannot be simultaneously here and there. Yes? So you know that, but which one I should accept? This one or that one? So how should I predict? By the way, I can write another answer for you. Let us check. Let us check. Let me give you this answer. Let me ask you to do this. X equals to 3 sine omega t plus 5 cosine omega t. It's more complicated function now. Let us calculate x prime t. Okay, what is x prime t? The derivative of this one is 3 omega cosine omega t, and then it becomes minus 5 omega sine omega t. Please correct me if I am making something wrong. And then the second derivative is what? It becomes negative 3 omega squared sine omega t. This becomes negative 5 omega squared cosine omega t. Yes? And now I can pull minus omega squared out. What is left for me? Yes? And then what is the name of this one? It's exactly x of t. So again, I have another answer. So now the poor system is actually confused. Because how, do you agree that, do you think that there is an important role for 3 and 5? Do you see in my calculation, can I change 3 to any number, 5 to any number? This calculation will remain intact. So how many answers I get? Infinitely many answers. So there are infinitely many possibilities for this equation. If this is the case, this equation, even though nice, it's completely useless. But we know that this is not being the case. So what is the problem? So mathematicians that don't care. All of these are solutions to this differential equation. But if this is going to predict something about my system, of course mathematicians also care about that, but I'm just trying to say what is going on. So can you tell me what is going on then? I hope that I could convince you that at least immediately we are able to see that there are infinitely many functions that satisfies this. Might be you say that, okay, by the way, sine and cosine functions were a reasonable guess. But how should we know that there are no complicated functions that satisfy the same property which we are not aware of yet, yes? This is also a possibility. Okay, how we can solve this problem? Why do you think, where is the flaw? There is no flaw in these calculations. All of these are intact. But so how do you solve the problem? This predicts something. This predicts the motion is not unique. Do you think it is really, really false? Is it really wrong that this motion is not unique? Because according to our prediction, at the level of the function, predicting the function, we have infinitely many functions satisfying that equation. Yes?
The motion is not the equation show the same motion, but the starting point is different.
Yes, very good. So, okay. So, a starting point is different. So that's completely correct, because is this equation that I have written here sensitive to initial position of my particle? This equation, assume that instead of starting the motion from here, instead of stretching it and releasing it from here, I squeeze it and start from the other side. Do you think something will change in this equation when I want to write the equation? Yes? Yes or no? The differential equation is sensitive to the initial condition or not? No, the differential equation is not sensitive, because x at 0 is not appearing here. So the equation itself is not sensitive to this. But is the motion sensitive to initial condition? It's clear, yes? Because if I started from here, at initial instant of time, my particle here is here, a little bit later the particle is here. But if I start from here, the particle is now here, a little bit later would be there. Yes? So the differential equation that I am writing here is not sensitive to the initial condition. Okay? And there is another, so it means that I have to fix this initial value. Is that understandable? I have to fix this initial value. So the reason that I have this mess, because I haven't fixed for my system where the initial point is. For example, the initial value x naught is if I accept this solution, what is x at 0? Sine of 0 is 0, which is not this motion. Because this starts from here, not at the origin. Yes? If I put this equation in cosine, it becomes 1. If this is exactly 1, that is good. But if it is not 1, this is not good. Yes? So do you understand? So that's exactly. This is the reason that you are getting this mess, because actually there is not one unique way of moving this particle. It depends to the initial conditions. I want to say conditions, because just fixing, this is what I want you to understand. Just fixing the initial position still will give rise to infinitely many solutions. Okay? It is not fixed completely. You need something to fix something more. If you want to have a unique way of motion, the initial position is one of those things that you need to fix for the system. But if you fix this one, you cannot, still you have infinitely many solutions. Okay? So, for example, let us fix that one. Okay, how should I do that? I would say that, do you agree with me? So that was my equation, x double prime of t plus omega squared. Let me write it minus omega squared, x of t. Okay, let me present this one for you. X of t, let me write any constant that I like, multiplied by sine omega t, and plus b times cosine omega t. Okay, I hope that you agree with me. Let us forego the calculation again. There is nothing particular about a and 5. This was 3 and 5 in the previous one. You can just solve this one. And then if you solve that one, you get minus omega squared x of t. Just take the derivative 2 times this becomes. So how many unknowns you see? 2 unknowns. So it means that one condition is not enough, because one condition, one initial condition, is one extra constraint, will fix one of these constants. The reason that there are infinitely many solutions again, because there is another constant. So this is why if you want to fix both of them, you need to give me the initial position of my system and, can you complete it? Yes?
The initial velocity.
Exactly, thank you. Do you understand that? So by giving you the initial position and initial velocity, I will tell you what are the values of A and B in a fixed way, and then there is a unique way of this particle moving. It's clear, yes, by the way, it's from physical point of view clear. Let me take it here, but instead of releasing it, releasing means what? Initial velocity is 0, I'm just releasing it. But instead of that, let me kick it from the same position, but the particle moves differently. Do you understand? So this motion is not just sensitive to the initial position, it's also sensitive to the initial velocity. But there is another question. Is this motion sensitive to something else? According to Newton's law, no. Because what is the degree of this equation? What is the order? Sorry, degree is the wrong word. What's the order of this differential equation? The highest order derivative is 2. And it means that the general solution includes only 2 parameters. Okay? So, if Newton's second law is the translation of nature, we don't need more than 2 pieces of information, but exactly we need 2 pieces of information to make the equation, the motion a unique way. Is that understandable? And so from now on, remember, if you want to predict the future of a particle, not only you need to know the rule, the law governing the system. If the system is Newtonian, the way that we actually experience every day, I need to give you the initial position and initial velocity. If I give you these 2, then you can solve the problem. Yes? Yes? So that is the initial law. Is that understandable? But you haven't seen this probably in physics. Is it familiar? You have solved, I don't know, the pendulum problem, or pendulum problem is harder, but you have seen this system in physics, haven't you? Okay, let me tell you something. This is definitely you remember. Do you remember in mathematics when I was talking about this? Of course, it was a long time back. We talked about these functions, yes? A sine x plus b cosine x. Do you remember I was able to write it in a different way? Do you remember anything at all? These functions can be written as, yes? You don't need to remember the whole details, but what was the rule?
Square root of
yes?
A squared
A squared plus b squared, and then you have cosine or sine, for example, x plus some number phi, yes? And this is in physics clear, yes? This is in physics people write it as a number a sine omega t plus a constant. Definitely you have seen this in physics. So that is exactly solving the Newton's equation for this system. Do you remember this is a wave function? I don't know, have you heard about these things a little bit here? So it is it's the motion of harmonic oscillator. This is called harmonic oscillator, yes? And that is the equation that you got. So what I wanted to talk about, I wanted to present this thing to you. So I want to say that differential equations is super important because if you cannot solve this simple differential equation, you don't know, you cannot predict. And if you cannot predict, so what is the whole point of science? Yes, you want to see the future by this. But of course, this also from physical point of view, it should be clear for you that something is missing. The law tells you, but you need to know the initial state to be able to predict the future. If you don't know anything about the system right now, you don't know what is happening for the system right now, how do you want to predict the behavior of the system in the future? So it means that you need to know the initial state of my system and then be able to predict the future. But according to Newton's second law, because of those things that we saw, the derivative that appears in the differential equation is of order 2. So it means that I need to fix two things in my state: the position of my particle and the velocity of my particle. If I give you those pieces of information, then you can predict this uniquely. You can predict where this particle is at any instant of time. So is that clear? Yes? Now let me tell you something also here about physics. Assume that I give you the initial velocity and initial position, and then you have this second law, and then you make sure that you are not making mistakes in your calculation, and you calculate and solve it, and then use this to predict the future of the system. What do I mean? I mean that you calculate what happens for x at an instant, for example 5, you get something, and then you go there, and when you measure, of course this is not happening, but assume that you measure and see that the particle is not at the place which is predicted by this, then what is your conclusion? Yes?
The equation is wrong.
Can you, yes, more or less right, but can you say what do you mean exactly by the equations are wrong? So mathematically I haven't done something wrong. So it means that probably the law which governs the system is not the second law. Okay? So it means that the problem of physicists should start to look for a new law for the system. Yes? But these deviations doesn't happen very frequently. So it didn't happen. So Newton wrote this formula, and it actually was successful for around 300 years. So we couldn't find any discrepancies. When the technology, so if you want to do the same thing, for example, assume that this is an electron, and of course this can be intermolecular forces. You can imagine it by modeling that. If you want to solve this model and predict where the electron is, the same thing will happen. So it means that this formulation of nature is not the final one, because it doesn't work for the electron, for example. And then it means that we have to change the whole physics to a new physics. Do you understand what I mean? These are very important concepts. You need to have a good idea of what is going on. So the take-home lesson is that if you want, I would say 99% I think, if you want to predict the future of a system, you need to solve the differential equation. And I don't think that I can overestimate that how important is that if you want to see the future. Yes? So you need to solve a differential equation, and the bad news is that for most of the differential equations, we cannot solve them exactly. But the good news is that actually we can solve them to any desired accuracy we need. Yes? So that was just general ideas of differential equations. But I think, yes, I will stop here, and then I will start mathematically thinking about how can we solve these problems. Of course, you will not touch this problem at the high school level, but that is a very simple problem when you go to university. So that is one of the equations that we can solve exactly. Actually, we did it, but we didn't solve it. We guessed the answer. We cannot rely on that, because if the equation is a little bit more complicated, how can we convince ourselves that what is the solution? But if I ask you what is the solution to this, actually you found all the solutions. The solution is written here. Yes? This is also strange. This is red, but writes blue. Okay, so this is actually the general solution of that one. And this one is a general solution because it includes two free parameters, and the degree and the order of my differential equation is 2. But can I say this is a solution? The answer is yes. Is cosine a solution? The answer is yes. But this is the general solution. It contains two free parameters. Yes? Okay, no questions? No? Okay, we stop here and continue tomorrow. Tomorrow we will actually mostly start thinking how to solve these differential equations, but not the second order ones. In Math 5 we talk a little bit about the first order differential equations in which the derivative is, the highest derivative is 1, and of course these are constants as before. Okay? Thank you.